This video, I want to tell you about a couple of projects that are related, actually, that I've been working on. They both deal with the ARM Thumb 16-bit instruction set for version 7 and 8. I know that's pretty specific, but it applies. So the first thing, the quickest thing I want to tell you about is I made a new atlas. A while ago, made an atlas similar to this for the 32-bit instruction set for ARM. It was definitely an eye chart. This one still may be an eye chart, but it's not nearly as much. What you're seeing on the screen right here is actually the entire 16-bit thumb instruction set. It doesn't cover the 32-bit, although there's an area down here where you can see where the 32-bit instructions would show up. So it has one more thing than the previous atlas had. In this case, you still do have the instructions and you have the instruction bit fields color-coded as well. But the thing that I added is on the right side here, you have a mapping of where these instructions fall byte by byte. So you kind of get an idea of how much of the bit space each instruction takes up. A great example is the memory operations. So storing a register or loading a register from memory or to memory. It takes up a good maybe third to almost a half of the byte space, which kind of shows an indication of how important that instruction is. You want to keep it pretty flexible, have a lot of different encodings for it. That's pretty much all the time I'm going to spend on this part. I want to show you something actually cooler that I've been working on. So it's a tool called ThumbSlicer. It kind of looks like this at first. What you can do from this point is just start typing some assembly instructions. So in this case, I'll just start typing like an add instruction. And you'll notice it's kind of changing as I type. In this case here, you can kind of see different encodings for an add instruction. The great thing, a couple great things. One, it's color-coded and it corresponds to, the machine code corresponds to the assembly. So the ones and zeros, you can see how they apply to the assembly. In the case of, let's say, just the first instruction, you can see the add in red. Those ones and zeros that are red represent that encoding for add. You can see the white against yellow ones and zeros. That's all zero, represents register 0. Next, you can see the black on yellow, the 011, that represents 3 or register 3. And finally, the yellow on black, the 001, that represents 1, which is register 1. You can kind of see how that breaks apart. And then the last half part of it, you can see the immediate value encoding, and you can see that in green right there. And then finally, the last part, this is where it's really kind of useful. It kind of highlights a complicated, in my opinion, encoding of add and then two registers that give you the ability to encode all 16 of the general purpose registers. Because in thumb mode, in general, you can expect to encode for registers 0 through 7, but not always 8 and on. But there are some exceptions where you can encode all of them. But the weird thing about this kind of encoding, and I'll highlight it in the atlas or I'll kind of mouse over the atlas area, it's talking about this encoding up here. So you have the ones and zeros there, and you have this weird 1 bit right here, and then 4 bits for one of the registers and 3 bits for one of the other registers. Well, this bit here actually applies to that RD register. So if we come back over to ThumbSlicer, this last instruction there, you can see this R3 is pretty intelligible. You see the 0011, but what's less intelligible is R1 is encoded actually by 0001. And one way to really quickly show validation of this is, let's just change that to R9 and R3. So now you can see more clearly 1001 is actually 9. So R9 is encoding of that. So kind of clarifies machine encoding, which I think is cool. And kind of breaks out other encodings like branch. I think this is kind of a cool example here. We can see not only different types of branching for different versions of ARM, but also how don't care bits are highlighted. So I'll go specifically into this ARM version 8 encoding, and you kind of see this NS in pink. Maybe the color is hard to distinguish here, but on some terminals it's kind of a more distinguished purple. And then this bit all the way down the line here is representing the NS part of this branch exchange. So that 1 bit only really applies to version 8. Now these white ones and zeros, or gray on some terminals, they can be anything. Like if you actually change these ones and zeros to anything, it doesn't change what the instruction does at all. Now in version 7, this pink or purple or whatever bit all the way down the line, that would also be a don't care bit. So that's the difference. And we can look at an instruction like push, and you can kind of visualize all the different ways we can do pushes and how that is represented in encoding. We can look at conditional branching, like branch if equal, branch if not equal, But then another cool thing is you don't just have to type assembly language. we can go to a different mode here, and what I just did is I typed the @, which is represented up here for the ASCII hex. So then I can just start typing machine code like that, DC03, and it corresponds to the ASCII hex part and gives you what that would be in binary and assembly. So you can kind of type machine code in ASCII hex. You can also do it as an integer, which I don't really see the point of too much, but you know, you can. So that's me typing 1, 2, 3. Those are all the instructions that would have digits that start with 1, 2, 3 if you look at it in the context of an integer. But my favorite mode is binary mode. You know, save the best for last. So let's look at an instruction that really flexes this the best, and that's going to be the logical shift left versus a specific move immediate 5 encoding. So in this case, I'll just start typing out some zeros. Those moves are already there. Start typing out some 1s and 0s. And in this case, I'm going to say move and then to register 7, you know, all ones there. And then whatever registers after that. Well, so the cool thing is this encoding shares some space with logical shift left. If we make one of the zeros right before those ones, anything else, it's going to be logical shift left. So let me go over here and just make that a 1. And then, you know, register 7 again. So in other words, that immediate 5-bit value, if it's anything other than 0, we're dealing with the logical shift left. But if it's zeroed out, that actually makes it a move instruction, which kind of makes sense logically. If you think about it, it still is a logical shift left. But since we're not shifting by anything, you know, immediate value of 0, so since we're not shifting by anything, effectively it is moving. So you can kind of think of that however you want. And finally, let's do another, one more encoding here. I'm going to do in binary 1, 0, 1, 1, 0, 0. And then it's going to look like it's not working for a second. And then I'll do a 1 right here. Now I'm going to switch it to regex mode. So this is the CBZ encoding. This one is encoded weirdly. It's kind of small on the map here, but there's a green bit. It's the I bit. It doesn't matter what bit that is in order to be CBZ, but this bit right here has to be a 1. But if you look at below the SXTH encoding, you know, there is a 1 here, but this is a 0. So if you're like typing this out kind of linearly, you won't notice that CBZ can kind of span or skip over the byte space area. It's probably one of the smaller areas of the map here, but you know, down here in this darker purple, we have, you know, add, subtract, and then we have CBZ, and then we have all these instructions that are too small to read. It's, you know, it's SXTH, SXTB, and so on. And then this next area right here, we have CBZ again, and it's actually the same encoding. These two different CBZs represents this same encoding because we have it like a bit here right in the middle. But with regex, we could represent it. We can say that bit is going to be a 0, 1, and then the next one has to be 1. So it's not just because I like regex and I'm finding an excuse to use it. This is a practical reason to use regex when typing out the binary for machine code for your instructions. Now finally, I'll get to the actual reason that I wrote this tool in the first place. I'm going to give it a well, before I do that, let me cat out my whitelist. It's just a comma separated list of characters. So this is my whitelist. In this case, just to tell you, these are all printable characters. Some of them I hex escaped, you know, whatever. So I'm going to use ThumbSlicer again and use a whitelist of the printable characters. And we see our normal interaction here again. I can start typing a move instruction type thing here. And notice that I have move and then R0, and then I don't have all the next operands here. I have R4, 5, 6, 7, 8, 9, but I don't have R0 through 3 or anything after R9. So the reason for that is if I use any of those encodings, you know, if you look at this bit field here, if we were to have R0, this is all zeroed out, that'd make this whole 8-bit value an unprintable character. And you can see your ASCII hex over here, but you can also see it in actual ASCII. In this case, 20 is a space, so it looks like nothing here. But literally any instruction we type out right now is going to be a printable character. It reduces us to that. So, you know, I could type any other character like, you know, str, you know, all the stuff we have here, if you look to the side, they're all printable characters, which is great. If you wanted to get real crazy, we can make that a blacklist. So here we go. Here's some instructions again, but now in this case, it's going to be instructions made up of all unprintable characters. So, you know, I'll type a move again, I'll do R0, and then notice we have are 0, 1, 2, and 3. It's the ones that we didn't have before. You'll notice the ASCII part here, it's all dots, so not like an actual ASCII dot, but it's representing unprintable characters. So what's the point of this? Well, for me, I'm probably using this not the way anybody else would use this. I have my own reasons for having this tool, which is why I created it. But for the people that may want to write something like shellcode, I could think of some reasons why this might be useful. When you write shellcode, you can't necessarily use the entire character space in your shellcode. It has to be an input to some application, and some applications don't take certain inputs. The biggest one being null, because usually when you're typing an input, it might be represented as a string, and usually strings are represented as null terminating, so once it hits that null, it thinks it's the end of the string, which would be the end of your shellcode, which you can see why that'd be a problem. But sometimes other characters can be problems too. So normally, I believe what people do is they write their shellcode, probably in assembly language first, and they write it logically how they think they want it to run with whatever registers they want to use, and then when they get to the end, they'll see, well, maybe we have a couple bad characters, some null bytes here, maybe some other characters we want to remove there, and then get creative about removing those null characters or whatever bad characters. So the point of using a tool like this is just not using those characters to begin with. So let me show you something here. Let's do a move R3, R4. Now, you'll notice there's actually two different ways to encode this. The second one, which actually is probably not going to be the encoding if you type this all in assembly, the second one is typically meant for registers that are higher than R7, but not necessarily. There actually is there's another difference here, whereas the first encoding actually acknowledges status flag outputs, like the N or the Z flags. They'll actually get written to the flag register. That actually can't be said for the second encoding. It doesn't do that. But regardless, you're probably not going to be giving a crap about the flags of a move instruction. I mean, maybe you are, but usually it's more like compare or test or whatever, right? But in this case, there is a huge difference between the two as far as the character space it uses. One does have a null, the other one doesn't. But I mean, that's not the only thing you have to use this for. Say you wanted to move a value into R1, and not all of these are printable. And say that the value is, I want to move, let's say the value is, I don't know, 55. And say R1 doesn't do it for us. Well, I can go back, but 55, that part's important. I can go back and say, R digit, just to give us a 0 through 9 in this case, and then say 55 and put us in regex mode. There we go. Now we can see encodings for all the various registers with that value. Gives us the flexibility to see real quick, right away, what machine encoding and ASCII character set it takes. These may not be the best examples to illustrate what you may be doing with shellcode, but that's not my thing right now. That's not what I'm doing. I'm usually just more interested in the low level. I like encoding, and I also like self-modifying code, which that's a whole different topic. I've been playing with that, manually flushing the instruction cache and all that annoying stuff. But that's a whole different story. That's what I'm into. But if you're into shellcode, I could see how you might use this as well.